So we're going to take a look at our second exam, and I'm going to go through the problems um, to just go over a few things that might have caused difficulty for people on this last exam. So our first question was the derivative question. You had four of them, and we had to find the first derivative of each of the items. This is probably the most sophisticated part of the exam, since we had to take derivatives in a very specific way. So our first problem was that we had f of x is equal to the cosine of x all over x cubed. And there were really two ways you could do this. One way was to use the quotient rule. So in which case, if you're taking the derivative of f of x all over g of x, you would do g of x times f prime of x minus f of x times g prime of x all over g prime of x squared. And this was really a more consistent way of doing it. You just had to sort of identify the top and the bottom, um, or if you were doing the high d ho business, you needed to identify which was the high and which was the ho. And so f prime of x in this case is going to be ho d high, so x cubed times the derivative then of the cosine of x, and then minus the cosine of x times the derivative of x cubed all over x cubed squared. So this gives you x cubed times negative sine of x minus the cosine of x times 3x squared all over x to the sixth. And I ask that you not simplify your answer, because it made it a lot easier for me to check when I was going through, did you have the x cubed, did you have the negative sign, did you have the 3x squared, did you have the x to the sixth. An alternative way would have been to use the product rule, and in order to use the product rule, you would have needed to rewrite the problem. So that's doing d dx of f of x times g of x, and then you would do f prime of x g of x plus g prime of x times f of x. And so in this case, I would rewrite my f of x as x to the negative 3 times the cosine of x, and then do the product rule on that. So f prime of x would equal negative 3 times x to the minus 4 cosine of x minus x to the negative 3 sine of x. And that was perfectly fine as well. You would end up with exactly the same answer, believe it or not, if you went through the algebra and you simplified it. Our next question was the f of x is equal to e to the negative x cosecant of 2x, so part B. F of x is equal to e to the negative x cosecant of 2x. And what's important here is that you understand that you're dealing with an inner and an outer function. One technique that might be helpful is if you were to make or do some sort of a substitution for your inner function. So for example, if you recognize that x cosecant of 2x is your inner function, go ahead and make that like u of x. And it helps to clean up the problem a little bit. And we're including the negative in that. So it helps to clean up the problem a little bit. And I'm going to write it on the side here, where u of x is equal to negative x cosecant of 2x. And then this way we can sort of look at these two things separately. Because if I apply the chain rule here, I know that I'm going to take the derivative of the e to the whatever first. And so that's going to be e to the ux, but then we're going to have to multiply by u prime of x. And I think this is where some of the difficulty seems to come in, is it's like keeping track of where the u prime has to go. So coming over on the side of my paper here, I'm going to find u prime of x, and I have to use the product rule in this case. So I'll have negative cosecant of 2x and then minus x. And when I take the derivative of the cosecant, remember that this is not just the cosecant of x, it's the cosecant of 2x. And so you will have to use the chain rule here as well. So on the side again, the derivative of the cosecant of 2x is going to be negative cotangent of 2x, cosecant of 2x, and then I have to take the derivative of what's inside, which is 2, and so all together I get negative 2 cotangent of 2x, cosecant of 2x. And so I'm going to put that in here as plus 2x cotangent of 2x, cosecant of 2x. And so when I go to express my derivative here, it'll be e to the negative x cosecant of 2x times then negative 2 cotangent of 2x, sorry. Oh, nope. See, I got mixed up. So negative cosecant of 2x plus then 2x cotan of 2x cosecant of 2x. And that would be the entire derivative for you. I think keeping track of your inner and your outer function can sometimes be the difficult part, but you have to find some way that sort of works for you. The next one was g of t is equal to the square root of natural log minus t squared. So g of t is equal to the square root of the natural log of t minus t squared. And again, we have to use the chain rule here. So I'm going to make this here my inner function. And so this is now equal to the square root of u of t. And I'm going to put on the side of my paper what u of t is in a moment. So when I do g prime of t then, I'm going to rewrite this, before I do g prime of t, let's rewrite g of t as u of t to the 1/2. So we're going to have to do the chain rule on this. So g prime of t is going to equal 1/2 u of t to the negative 1/2 using the power rule, and then multiplied by u prime of t. So I'm going to come over on the side of my paper and find u prime of t, which is d dt of the natural log of t minus t squared, which is equal to 1 over t minus 2t. And so altogether, this is now equal to 1/2 the natural log of t minus t squared to the negative 1/2 times then 1 over t minus 2t. Our question D, going back up, was the arc secant of x squared, and you were given a formula for that. Y equals the arc secant of x squared. And the formula is that if you find the derivative of the arc secant of x, this is, or arc secant of u. So the formula that was given on the test was already written using the chain rule, essentially. And so you would have u prime all over the absolute value of u times the square root of u squared minus 1. So in this case, our u is equal to x squared. And so that means that dy dx, or y prime, however you wanted to notate it, was going to then be x squared. I'd plug in x squared for u, so you'd have x squared prime all over the absolute value of x squared times the square root of x squared squared minus 1. And you do have to simplify the derivative at the top so that you get 2x. Also, one thing that you should observe for the future is, since x squared is always going to be a positive number, the absolute value is kind of not necessary. And so I'm going to make this now x squared, the square root of x to the fourth minus 1. I'm going to leave it like this, even though it's not simplified, because this is a completely fine answer to respond with. The next problem was the linear motion problem. And so one thing to keep in mind that the main tools for answering this was not really any physics as much as it was a relationship. So if S of t is the location or the displacement, it's not really the location. It represents the displacement. So it doesn't tell you the total, it does tell you the total displacement of the object from start to finish. The velocity is then the derivative of the displacement. And remember, that's because velocity is distance per time. So that's a ratio, right? If you do s of t minus s of 0 all over t minus 0, the units of the numerator are going to be distance, and the units of the denominator are going to be time. And so when you have distance divided by time, that's a speed. And then the acceleration is how quickly things are changing in what direction. So that's the second derivative of s of t, which is equal to the derivative of the velocity. So that's the acceleration. And so those are the main tools you needed to know for this, and then be able to know, well, what is the question asking? So the first part of the question is find the distance traveled by the train in 2 minutes. And so since the total distance is characterized by s of t is equal to 1/4 t squared plus t, that means that s of 2, which is in minutes, is going to be 1/4 times, or that's negative 1/4, my apologies, negative 1/4 times 2 squared plus 2, which is going to then be negative 1/4 times 4 plus 2, which will equal negative 1 plus 2, or 1. And this is going to be in miles, because in the problem, they told us that t is given in minutes, and s of t and s is given in miles. So that means in 2 minutes, the train is going to cover 1 mile, which is a very fast train. And then, so then part B is saying what was the train's acceleration at time t equals 2 minutes? Does this indicate that the train was slowing down? I didn't actually even read the problem. A train is cruising when suddenly the engineer notices a cow on the track ahead of the train. The engineer applies the brakes, causing constant deceleration of the train. The total distance at a time t in minutes traveled by the train after the brakes were applied is given by s of t equals negative 1/4 t squared plus t, where s is given in miles. So now we know what was we want to know what was the train's acceleration at t equals 2 minutes. So I need to find the second derivative of s. So the first derivative, which is the velocity, and you will need that at some point in the problem, will be negative 1/4 times 2t plus 1. And so that's going to be negative 1/2 t plus 1. So that's the velocity. And I'm going to rewrite that as v of t. And then the acceleration is going to be the derivative of that, which means I need to now take the derivative of negative 1/2 t plus 1, which is going to equal negative 1/2. So the acceleration is negative 1/2 mile per minute squared. Those are the units that are applied for velocity, for acceleration. And this indicates that the train was slowing down, because it means that the speed is gradually getting less. So it indicates train was slowing down. So it confirms the problem altogether, where it says, was there deceleration? And we also can see that it was constant, right? Because this doesn't depend on t. So at t equals 2 minutes, it's going to be negative 1/2, and so the train was slowing down. The next question is, if the cow was 1 mile ahead of the train the instant the engineer applied the brakes, did the train come to a stop at t equals 2 minutes? So a couple of things, you have to put part A and part B into together. Part A, we know that the train is going to travel 1 mile in 2 minutes, regardless of any of the mitigating circumstances. Whether the train was slowing down and what how fast it was going is going to sort of be still encapsulated with this formula here. So we know that in 2 minutes that the train is going to travel 1 mile, and that's exactly where the location of the cow is. What I'd like to know, though, in order for the cow to be safe, is whether the train came to a stop. And so in order to determine whether the train came to a stop, I need to determine what the velocity was at 2 minutes. And so we have a formula for the velocity, and so I'm going to plug 2 into that formula for the velocity. And what I get is -1 plus 1, which is equal to 0 miles per minute. And so that means that the train was stopped at the 2 minute mark. So train stopped and traveled 1 mile. So cow should be safe. Maybe it got touched. I don't know. We just know that the train didn't run over it. It was stopped by the time it got to the point of the cow. Question number 3 was our implicit differentiation question. And in this particular problem, we're going to let y equal a function of x. This is not something I expected you to write in your problem, but for the purposes of doing it, I'm going to make sure that I put it in just for your benefit so that you can remember that you have to do whatever in order to solve it. And remember that y is a function of x. It isn't actually the variable that you're differentiating. And so I'm going to take the derivative then of both sides of this problem in order to find dy dx. And that's going to give me 2x. And now I'm going to have to use the chain rule here because I have to take the derivative of the outer function first. So that gives me 2y of x. But then I also have to take the derivative of the inner function, which is going to be dy dx. And then likewise here, I'm going to get 4 times the derivative of y, but I don't know what y of x is because it's implicit. It means it's an implied function, that I don't have a formula for it. And so I can't write the derivative as just 4. I have to write it as 4 times whatever dy dx is going to be. I'm going to drop the y of x now, so this is going to be the following, and I'm going to solve for dy dx. So I'm going to do that by moving the 2y to the other side, and I'll just do it in multiple stages. And then I can factor out a dy dx from this. At which point I can then divide by 2y plus 4 in order to get my dy dx. And so dy dx is equal to 2x over 2y plus 4. I had made a mistake in my comments to the class, and I'll explain that in a moment, but on your grading, make sure that you have at least this formula in order to receive full credit for part A. For part B, I was pretty generous with, because we didn't do a whole lot with this, but a vertical line has undefined slope. And so when I say determine the points x, y where the graph has vertical tangent lines, I'm looking for where, so looking for where dy dx is undefined. And so this is why I think this problem was could have been bordering on unfair, is because we didn't really do much with this. So you have to take 2y plus 4 because that's the part of the rational expression. If you want where something is undefined, you need the denominator to be undefined. So you get 2y plus 4 is equal to 0, which means y is equal to negative 2. And then you need to find x. So in order to find x, I need to take that value of y and plug it back into my equation, which is x squared minus y squared is equal to 4y. And so that's going to be x squared minus 2 squared is equal to 4 times minus 2. Or x squared is going to equal, I think this is going to be positive 4? No, negative 4. Hold on, something's not right. At which point you get x squared is equal to negative 4, and so there's no solution. There's no real solution. They're imaginary solutions, but we're not dealing in imaginary, we're dealing in real calculus, and so that means there's no such point where graph has a vertical tangent line. If you took, because this is so different than any of the questions that you had previously, if I should have given at least 5 points for setting either the numerator or the denominator equal to 0. Actually, I should have given full credit if you took either the numerator or denominator to equal 0. 5 points generally came off if you got to a point and you just sort of stopped. So make sure that you go back and you understand. The main thing I need you to get out of this is that a vertical line has an undefined slope, and it's that recurring theorem, that recurring idea that if you have a rational function, like you have f of x over g of x, if you want to know where the function is equal to 0, you set the numerator equal to 0. And if you want to know where it's undefined, you set the denominator equal to 0. So for this to equal 0, numerator is equal to 0. For undefined, you set this equal to 0 and you solve for that. And that's going to come up a lot. We're going to have to practice that continually. The next question is f of x is equal to the tangent of 2x. Determine the equation of the tangent line to f of x around x is equal to 0. I'm going to write down the formula for the equation of the tangent line first, and it is something I would strongly recommend committing to memory. So this will be y minus f of a is equal to f prime at a times x minus a. Sometimes you would do this for the implicit derivative, and in which case this would be dy dx at a particular point. So this means that in this case, since I want to do it for x is equal to 0, this will be f of 0 is equal to f prime at 0 times x minus 0, or y minus f of 0 is equal to f prime of 0 times x. So it tells me a couple of things, that I need to find f of 0 and I need to find f prime of 0. F of 0 is going to equal the tangent of 2 times 0, which is going to equal the tangent of 0, which is just 0. And we can remember that because if you think about the graph, I mean, you can think about sine and cosine, of course. on the unit circle, but the graph is actually easier in this case. The graph of the tangent looks like this, where this is negative pi, this is positive pi over 2, and this is negative pi over 2. And so you can see that the graph passes through 0 at the point 0. F prime was another issue, because we had to use the chain rule, right? We had to take the derivative of the outer function, which would be secant squared of 2x, and then we have to take the derivative of the 2x, which is just going to be 2. So we would have 2 secant squared, and f prime of 0 is going to equal 2 times secant squared of 2 times 0, or 0, which is going to equal 2. So the slope is going to equal 2 at this point, and so plugging those in, this means that my tangent line will be y minus 0 is equal to 2x, or y is equal to 2x. And I want you to understand what this means in this context. It specifically is telling you this, that in a neighborhood of x is equal to 0, so you're in a small interval around x is equal to 0, the assumption we can make then is that the tan of 2x is approximately equal to 2x. The way this is generally done in a physics class is that this will be told to you that when x is small, you can just make this approximation. But the reason we do is because of the tangent line. So when x is small, or x is close to 0, like 0.1, 0.2, those sorts of things, when it's a small number close to 0, that means that we can replace the tangent of x with 2x. And so that becomes important in question B. You didn't have a homework assignment on it, but there was a pretty big deal of a problem in the video that was done. So I would go back and watch that if you found this difficult. I know several of you wanted to do the regular method that you learned from the previous chapter, but that's not what the question asked for. And so you wouldn't have received credit for it, regardless of whether it was correct or not. The question specifically said, using A, evaluate this limit. It didn't say use a special limit. It said use part A. That is, so I have to use the tangent line. And so in order to be able to do this, you have to remember what is meant by limit as x approaches 0. And this is not just me saying this in order to make life difficult. It's so that you can remove this idea that limits have some special operational power, which they don't. It's an idea, and that's what makes them hard. Remember that when I have this would be akin to me saying, what is the value of x all over the tangent of 2x for values of x, or for x near 0, or in a neighborhood of 0. Another way to say x near 0 is for small x. So what would be the value of x all over the tangent of 2x for small x? I'm asking you to make that approximation. And so if you can sort of not think about the limit as x approaches 0 as being like plug something in or do algebra, but think of it in terms of, I want to know what's happening for values of x that are really tiny, then this turns into a new problem. So in that sense, we know the following, that for small x, the tangent of 2x is going to be approximately, I'm going to say approximately, I'll leave it to the physicists to say equals, but for small x, the tangent of 2x is approximately 2x. And so that means then that x divided by the tangent of 2x is approximately x all over 2x, or 1/2, because the x's can cancel out. And so this means then that for values of x in a neighborhood of 0, x divided by the tangent of 2x is equal to 1/2. And believe it or not, this is the way real scientists tend to do these problems. They do not do special limits. Special limits have their place, but this is not one of them for these sorts of approximations. And also, real scientists very rarely will write this down. When they do, there's a specific reason that they do it. It's because there's no other way to write it. And when they do use the word limit, what they mean or what they're intending is that they're saying, all right, I'm looking at a small interval around zero, like from negative delta to delta. So negative delta to delta, where zero is in the middle of that interval. And so what's happening in that small interval? But in order to be able to do that, you have to remember that limit just specifically means that I'm in a neighborhood. And that's an important idea moving forward. The last question was, a conveyor belt is discharging gravel at a rate of 4 cubic feet per minute into a pile shaped like a cone where the radius r is 4 times as big as the height h. And I underlined that for a specific reason. We want to determine the equation of the volume of the cone at any time t in terms of only the height h. And then I wanted to know how fast will the height of the cone be changing the instant the height of the cone is 3 feet. So a few things to keep in mind. Drawing a picture is often a nice idea. So for example, if I have gravel falling, the cone, first of all, the cone is not going to be point down. The way that this cone is going to look is it's going to form a mound like this. And so the cone will look like this. The radius is measured from the bottom here, and then the height is measured from the center to the top. Perhaps the geometry of this may have given you some difficulty because you haven't seen how to measure the dimensions of a cone in a while. However, I did tell you that the volume of the cone would be given by 1/3 pi r squared h. And so the first part of this problem doesn't ask you to do anything with the numbers. It just says to put v in terms of specifically h. And we're in these types of problems, you have to assume that all of these variables are implicitly functions of time because they're all changing. Think of it as gravel falls, the height of the cone is going to be changing, but so too is going to be the dimensions, the radius, and what have you. So the reason this thing is underlined is because we have to use it in order to do part A. And the way that we're going to use it is as follows. The one thing you have to keep in mind that anytime you have any sort of word problem, you have to focus on what this word is means. If ever you read a legal document and something says that A is B, then that is a pretty strong statement because it means that A and B are interchangeable. They're the same thing. And so lawyers, when they see the word is, that's a big deal. That's one of the big deals. The other one is and. If you see an and sometimes a period can also be a big deal. But in this case, the is important. And in mathematics, the word is translates as equals. So if you want to, you can say r equals, that's not how you spell equals, equals 4 times the height. And so if you think of is as and equals as being two interchangeable words, now that makes sense. That r equals 4 times the height. And so I'm going to replace r with 4 times the height then, because they're the same meaning. And so when I simplify this now, I will get 16h squared times h, which is going to be 16/3 pi h cubed. And so now my volume is entirely in terms of h. It does not rely on h and r. And then the next part of the question was, how fast will the height of the cone be changing the instant the height of the cone is 3 feet? And explain your answer. So I'm going to make the implicit function assumption here because these are changing with respect to time. And so I am going to assume that v and h are functions of time. I'm not worried about any of the numbers, whether what the change in the volume is or what the height is. I don't worry about that just yet. Just worry about getting an expression of in terms of your variables, and then make sure that you can go back and do what you need to do. So I'll take the derivative and I'll get dv dt. The 16 pi thirds can come out, and I'll take ddt of h cubed. And so you have to use the chain rule here because it's an implicit function. So I get 6 pi over 3 times 3h squared, but then times dh dt. And so your new formula is going to be the following. I can cancel out the 3's. Your new formula will be dv dt is equal to 16 pi h squared times dh dt. And now we can go back and worry about what the things are. The question is asking how fast will the height be changing? And so that means dh dt is the variable. The other information that is given to us is that the gravel is falling at a rate of 4 cubic feet per minute. And so this is a change in the volume. When you have cubic feet per minute, the per minute means that it's changing. And it's increasing, so then it's not going to be negative. So this would be 4 over here. And we're finding this the moment that the height of the cone is 3 feet. And so we wanted the instant that h is going to equal 3. And so our equation is going to be 4 is equal to 16 pi times 3 squared times dh dt. So that's 4 will equal 16 pi times 9 dh dt. So 4 is going to equal 144 pi then, times dh dt, which means 4 over 144 pi is going to equal dh dt, or in other words, 1 over 36 pi, and this is height, right? So this will be feet, because we're in feet. So feet per minute is going to equal dh dt. I am okay if you did not simplify it to that point, but just be aware that there are other people in the math department that would prefer that you did. So, make sure that you understand how that is done.